Welcome to the Geek Investor podcast, where we dive into the fascinating mechanics behind cutting-edge technologies in the world's most investable companies. If you enjoy learning how tech works behind the scenes and where it might take your portfolio, don't forget to like, subscribe, and join us on this journey. Hosted by Ethan and Claire, and for full transparency, these are synthetic voices powered by Notebook LM. Okay, let's unpack this. Today, we're kicking off a deep dive into, well, a really cool area of AI. How deep learning lets machines perceive things, see, hear, maybe even understand us.
Absolutely. And our goal here in this deep dive is really to break down the core ideas behind machine perception, the stuff that's driving so many of those AI applications you hear about.
Right.
We want to get past the jargon, make it feel intuitive.
Exactly. How machines go from just following rules to something more like intuition about the world around them. It's fundamental tech for so much now. Self-driving cars, smart speakers, all that. So where should we begin? How about vision? How does a machine actually see? It's not like our eyes, I assume.
No, not at all. For a machine, an image isn't, a picture of a cat. It's just math, a grid of numbers.
Numbers?
Yeah, numbers. If it's black and white, each number is just brightness, maybe 0 to 255. For a color image, you've got 3 of those grids: red, green, blue values. So even a small image, like 28 by 28 pixels, that's already 784 numbers right there. Add color, it's triple that, just raw data.
Wow, okay, just a big block of numbers.
Yeah.
So how does it get from that spreadsheet, basically, to recognizing, I don't know, an elephant wearing a tutu?
Ah, right. That's where convolutional neural networks come in, CNNs. Think about how a kid learns. You show them pictures, right? Cats, dogs, maybe even elephants and tutus.
Yeah.
You don't give them a list of rules like pointy ears mean cat. They just figure out the patterns from seeing lots of examples.
Yeah.
CNNs kind of do the same, but they break pattern finding down into steps, into layers.
Okay, layers. And the first big step is this thing called convolution.
Exactly. Convolution. Imagine you have a tiny stencil, maybe 3 by 3 numbers. We call that a filter or a kernel.
Like a little magnifying glass.
Sort of. And you slide this little stencil over the image, one small patch at a time.
Okay.
For each patch it covers, you multiply the numbers in your stencil by the numbers in the image right underneath it.
Multiplying. Okay, got it. And then?
But you just add up all those results. That gives you one single number.
One number. What does it mean?
That number tells you how much the specific pattern in your stencil matches the pattern in that little patch of the image. You do this over and over, sliding the stencil across the whole image.
And what do you end up with?
You end up with a new image, sort of. It's called a feature map. And the bright spots on this map show where the pattern your filter was looking for appeared strongly in the original image.
Ah, so it's highlighting where specific simple patterns are, like edges or corners.
Precisely. Instead of trying to grasp the whole image at once, convolution focuses on finding these simple local patterns. Because complex things, like faces or cats, are just made up of these simpler bits combined.
Right, breaking it down first. Makes sense.
Exactly. And right after convolution, there's usually another simple step, ReLU.
ReLU, rectified linear unit. Sounds fancy, but I hear it's actually pretty basic.
Oh, it's super simple. If a number coming out of the convolution step is negative, ReLU turns it into 0. If the number is positive, it just stays positive. That's literally it.
0 or stay the same. Why do that? What's the point?
Well, it's like that fire alarm analogy you mentioned. Keep the strong signals, ignore the weak ones. It adds something called nonlinearity. Without steps like ReLU, the network, no matter how deep, could only learn very simple straight-line relationships. ReLU lets it learn much more complex stuff. It's basically saying, if this pattern match wasn't strong, just forget it. If it was strong, keep it. Keep the fire, drop the ashes.
Got it. Focus on what matters. Okay, convolution finds local patterns. ReLU cleans up the signal. What's next? Pooling.
Pooling, yeah. Max pooling is a really common type. You take another little window, maybe 2 by 2, across the feature map, and in each 2 by 2 square, you just find the biggest number and keep only that one. You throw the other 3 away.
Whoa, throwing away data, doesn't that lose information? Why do that?
It seems counterintuitive, right? But it does 2 useful things. First, it shrinks the feature map, makes things more manageable.
Okay, efficiency.
But more importantly, it makes the network a bit more robust to where exactly a feature appears. If max pooling keeps the biggest number from a 2 by 2 patch, it means the network knows that strong feature was somewhere in that little area, even if it shifts a pixel left or right.
Ah, so it's less sensitive to the precise location, like zooming out slightly.
Exactly. It's like saying, okay, I detected an eye-like shape in this general vicinity. The exact pixel doesn't matter as much as the presence of the feature. It helps recognize that cat, whether it's perfectly centered or slightly off, shrinking the picture, keeping the essence.
Keeping the essence. I like that. Okay, so you do some convolution, write LU, pooling, maybe repeat that a few times. What happens at the end?
Right? After several layers of this, processing the image into these feature maps, you take whatever map you have at the end and you flatten it out.
Flatten.
Yeah, just turn that grid of numbers into one single long list of numbers. That's your feature vector. It represents the image now, not as raw pixels, but as a summary of all the important features detected.
Okay, a big list representing features, and that list goes.
That goes into the final part, usually what are called fully connected layers. These are more like the traditional neural network layers you might picture. Every number in that feature vector connects to neurons in the next layer.
And these layers make the final call.
Pretty much. They look at the combination of features represented in the vector and essentially vote on what the original image most likely is. The final output is the classification.
Like, okay, based on these features, 94% confidence this is a cat.
Exactly like that. It gives you the prediction and usually how confident it is.
That's amazing. Just from numbers, through these steps, finding patterns, cleaning signals, summarizing it, can actually identify things. That's the bedrock for so much visual AI. Okay, that makes sense for static images, for vision. But what about sound? Sound isn't static, it unfolds over time. It's all about sequence. How do machines handle that?
Great question. Yeah, sound or language or even stock prices, they're different. They have a history. The past affects what's happening now. Like hearing footsteps. One footstep is just a sound, a sequence of footsteps getting faster. That tells you something important is happening.
Right, you need memory, context.
Exactly, and that's the idea behind recurrent neural networks, or RNNs. They're built specifically for sequences.
Recurrent, meaning they loop back somehow.
Kind of. At each step in the sequence, say, processing one word or one short snippet of audio, the RNN takes the new input and considers its own internal state from the previous step. This internal state acts like a memory.
Ah, so it's combining the now with the memory of the before.
Precisely. Think about understanding a sentence. If I say, because it started raining.
I grabbed my umbrella. You expect something related to rain because you remember the start.
Exactly. A simple RNN tries to capture that dependency by constantly updating its internal hidden state based on the current input and its previous state.
Okay, that sounds logical, but I've heard simple RNNs aren't perfect. Something about memory problems, like a short attention span.
Yeah, that's a good way to put it. They suffer from the vanishing gradient problem, which basically means they struggle to learn dependencies over long stretches.
Meaning
the influence of inputs from way back at the beginning of a sequence tends to fade out as new inputs come in. The memory gets overwritten or diluted too quickly.
So they might remember it rained to predict umbrella right after, but maybe not connect the first sentence of a paragraph to the last sentence.
That's the core issue. For really long sequences, a long conversation, a complex piece of music, a lengthy document, that short-term memory is a real limitation.
Okay, so how do we fix that?
That's where a more sophisticated type of RNN comes in. Long short-term memory networks, LSTMs.
LSTMs.
Right.
Heard a lot about those. They're designed to remember things for longer.
Exactly. They have a more complex internal structure specifically designed to combat that memory decay. The key is the memory cell.
A memory cell.
Yeah, think of it like a separate channel or conveyor belt inside the LSTM unit just for holding on to information over time. And crucially, LSTMs have these things called gates.
Gates, like controlling flow.
Precisely. They control the flow of information into and out of that memory cell. There are usually three main ones.
Okay, what do they do?
Well, first there's the forget gate. Looks at the new input and the previous state and decides which pieces of information in the long-term memory cell are no longer needed and can be, well, forgotten.
Clearing out old stuff. Makes sense.
Then there's the input gate. It decides which new information coming in is important enough to be stored in the memory cell.
Okay, deciding what's worth remembering now.
And finally, the output gate. It decides what parts of the memory cell, combined with the current processed input, should be used to generate the output for this particular time step.
So it's like actively managing its memory, deciding what to keep, what to add, what to use right now.
Exactly. Think of it like a researcher with a notebook. The forget gate crosses out irrelevant old notes. The input gate writes down important new findings, and the output gate decides which nodes, old and new, are relevant to answer the current question.
That's a great analogy, the notebook inside the mind.
It's that controlled gating mechanism that lets LSTMs selectively remember important information from way back in the sequence and ignore irrelevant stuff, overcoming the short-term memory problem of basic RNNs.
Wow, so they can handle much longer, more complex sequences, like understanding speech or generating realistic music.
Absolutely. LSTMs and similar gated RNNs like GRUs were a huge leap forward for processing sequential data effectively. They formed the basis for a lot of speech recognition and language tasks.
Okay, so CNNs for seeing static things, LSTMs for hearing sequences. What about the really tricky one? Understanding language, meaning intent, nuance. That feels like a whole different level.
It definitely is. Language is more than just a sequence of symbols or sounds. It's about concepts, relationships, context. How do machines even begin to grasp that?
Yeah, they don't start with a built-in dictionary, right?
Nope, they have to learn it. And one of the really foundational ideas here was word embedding.
Word embedding, what's that about?
Instead of just giving each word a unique ID number, word embedding tries to represent each word as a list of numbers, a vector in a sort of high-dimensional mathematical space.
A list of numbers, a vector, like coordinates.
Sort of, yeah. And the really cool part is that the way these vectors are learned, words that are used in similar ways or have similar meanings end up having vectors that are close to each other in this space.
Wait, so like king and queen would be near each other?
Exactly. And even more, the relationship between vectors might capture meaning. Like the vector difference between king and queen might be very similar to the vector difference between man and woman.
Whoa, you're basically mapping language onto geometry. That's wild.
It is. It captures semantic relationships numerically. Techniques like word-to-vec or glove really pioneered this. Suddenly, words had mathematical representations that encoded some aspect of their meaning.
Okay, that's a huge step. But understanding a whole sentence is more than just knowing what individual words mean, right? It's how they fit together.
Absolutely. And for a while, people used RNNs or LSTMs for that, processing sentences word by word, building up context.
Made sense, following the sequence.
It did. But then came a model architecture that just changed everything for language tasks.
The transformer.
The transformer. Okay, yeah, that name pops up everywhere now. What's different about it?
The biggest conceptual shift is that, unlike RNNs that process sequentially, the transformer looks at the entire sentence all at once. The whole sentence, simultaneously. How does that even work? Doesn't context build up word by word?
It does, but the transformer handles it differently. Its key weapon is something called the attention mechanism.
Attention. Okay, like paying attention.
Exactly like that, but mathematically defined. When the model is processing any given word in the sentence, the attention mechanism allows it to look at all the other words in that same sentence and figure out how relevant each of them is to understanding the current word.
Like a spotlight, focusing on the important context words.
That's a perfect analogy, a mental spotlight. Think about a sentence like, "The cat chased the mouse because it was hungry."
Okay, it refers to the cat.
Right, you know that instantly. An attention mechanism helps the model figure that out. When it's processing the word it, the attention mechanism will likely calculate that the word cat is highly relevant and mouse is less relevant for understanding what it refers to in this context.
How does it know which words are relevant? Is it learning that?
Yes, it learns it. At a high level, for each word, let's call it the query, it compares that word's representation against the representations of all other words in the sentence, the keys. This comparison generates scores indicating similarity or relevance.
Okay, scores for every other word.
Then these scores are converted into weights, usually using a function called softmax, that add up to 1. These weights tell the model how much attention to pay to the information associated with each word, the value, when trying to understand the current word, query.
So it's calculating for this word it, how much should I focus on cat, how much on chased, how much on mouse.
Exactly. It's dynamically weighing the importance of all other parts of the input sequence to understand the context of each part. There's some math involving queries, keys, values, and scaling, but the core idea is this dynamic, context-dependent weighting across the whole sequence.
Wow, so it's not just reading left to right, it's building this rich web of connections between all the words simultaneously.
Precisely. And that ability to weigh context across the entire input, not just relying on adjacent words or a feeding RNN memory, is why transformers are so incredibly good at tasks like machine translation, writing summaries, generating really coherent text, empowering those advanced chatbots we see now.
Okay, looking back, this has been quite a journey. We started with images as just grids of numbers.
Right, and saw how CNNs use filters and layers to find patterns in those numbers, essentially learning to see.
Then we moved to sound and sequences where RNNs try to remember the past.
And how LSTMs improved on that dramatically with their gates and memory cells, enabling machines to really listen and process over time.
And finally, tackling language itself, using word embeddings to give words meaning and space.
And then the transformer's attention mechanism, letting models understand context by looking at the whole picture, weighing the importance of different words.
It really feels like magic sometimes. How these mathematical operations, layered together and trained on data, allow machines to perceive and interact with the world in increasingly sophisticated ways. That's the core of so much innovation in AI-driven companies.
It truly is. Taking seemingly unstructured data pixels, sound waves, text, and finding the meaningful patterns within.
So as we wrap up this deep dive, we want to leave you, our listeners, with a few things to mull over, to really let these ideas sink in.
Yeah, maybe take a moment and think. In your own words, how would you explain what convolution does? And why is that specific process so helpful for recognizing visual patterns?
Or think about LSTMs. What was the fundamental problem with simpler RNNs that LSTMs were designed to fix? And how do those gates forget input-output actually achieve that fix?
And one more, on language. Consider that attention mechanism in transformers. Why is looking at the whole sentence at once such a big deal compared to processing word by word? What does that ability to decide which other word should I pay attention to really unlock?
Definitely some powerful concepts to reflect on. Understanding these mechanics really opens up how you see AI today.
And that brings us to the end of this deep dive on machine perception. We hope breaking down these concepts helps you see the how behind the AI headlines.
Join us next time as we continue digging into the technologies shaping investment opportunities and our future.
Until then, keep learning.